Transformations are something that we talked about a bit in some of the old videos, especially as it related to grade 10 curriculum, right? But we're really going to dive into it now in the grade 11 material, especially as it relates to all different types of functions, right? Not just something like quadratics, but really everything. To do that, we have to write a general form. So I'm going to write it as y equals a f bracket k bracket x minus d close bracket plus c. And you might be looking at this and you might say, that looks kind of familiar. Or you might say, I've never seen this before, I don't know what it is. That's okay. This is just the general form for writing out the structure of a function with all of its different transformations, right? If you do think this looks familiar, you might be thinking it looks a bit like vertex form. Like when we have vertex form for a quadratic, it might be something like y equals 4x minus 2 squared plus 3. It looks kind of like this, right? There's a bracket, you have a plus with a number on the end like that. So it does look a bit familiar, and that's exactly what it is. If this was a quadratic function, then we would be following this pattern in vertex form. Now I say if it was a quadratic because this f here allows this to be any function we want, right? This is the general form, remember. Well, what does that mean? Well, it means you could write this as a quadratic, so a, k, x minus d plus c, and this could be squared. That would make it a quadratic function, right? You could have y equals a square root k x minus d plus c, and that's a square root function, but it's the same pattern, right? You could have y equals a absolute value sign k x minus d plus c. Again, same pattern. So this f and then the brackets, those symbols can be swapped out for a square root, absolute value symbols, whatever you need, right? Those symbols can be swapped out for whatever we need, to make it whatever function we want. Now, we have to talk about what all these letters represent, right? And you might be familiar with some of them just from the fact that I said this is the same as, vertex form, right? And we know what some of those numbers do in vertex form. So that should give you a leg up here, actually. So if I want to talk about a, right? That a, again, it represents a number. What is that number usually responsible for? Well, that number is typically responsible for vertical stretches or compressions, meaning that your graph will get shorter and wider or taller and thinner depending on the a value. If the a value is greater than 1, we're talking about a vertical stretch. If a is less than 1, or actually more specifically, if a is between 0 and 1, right? If it's a fraction like a half or a quarter or 2/3 or something like that, that indicates that we have a vertical compression and your graph is getting shorter and wider. Now, what if a is less than 0, right? What if a is a negative? Well, if a is less than 0, right, a negative, that would mean that we have a vertical reflection. Or in other words, we're reflecting over the x-axis, right? So if your quadratic has a positive a, it looks like this. If there's a negative a, it looks like this, right? I think we all remember that from graphing quadratics, and it's the exact same concept for every other type of function. So that's what your a value does. Now your k value is very similar, right? It's being multiplied by the bracket just like how the a is on the outside. The only difference is the k is on the inside. So the k value we describe as being responsible for horizontal stretches or compressions. Now it's a horizontal stretch when k is between 0 and 1, and it's a horizontal compression when k is greater than 1. Now, if k is less than 0, right, because up here we said between 0 and 1, if k is less than 0 or negative, that means we have a horizontal reflection. Or in other words, we have a reflection in the y-axis, right? It reflects sideways, horizontally. We don't see that a lot with quadratics because quadratics are symmetrical, so you wouldn't notice if that number was a negative. It wouldn't really change your graph. But for some functions that aren't symmetrical, it's absolutely going to have an effect. So we have to be aware of that. Now you have your d value here, which we know accounts for horizontal translations, or you might call that horizontal shifts. That's how I like to refer to it. So if d is positive, bigger than 0, that means that we're moving to the right. And now you might be saying, wait a minute, that's the opposite of what I learned. Well, I'm saying negative d. So if just the d is positive, that means that overall this whole thing's negative. This is where things get a little confusing, right? So what I like to do is just look at the number that's here, right, next to my x. If it's x minus 4, that means 4 to the right, right? If it's x plus 4, that means 4 to the left. So I know I'm saying here d bigger than 0, you go to the right. When it's negative, it goes to the right, because I'm just talking about the d value. I'm not including that negative, right? This gets a little bit confusing, and I don't necessarily like the way it's taught. Just remember that if this whole thing together is negative, you go to the right. If it's positive, you go to the left. Basically, everything on the inside of the brackets, everything inside the function, works the opposite way of how your brain usually thinks it would work, right? Like a k value that's bigger than 1, well, that's not actually a stretch, that's a compression, right? If it's smaller than 1, that's a stretch. And if this d value here, if you have minus a number, that means you're moving to the right, when you would think that you would go to the left. But of course, we've talked about why this is. We've looked at the table of values, and we've seen how the points are affected by these symbols and by these signs, and so we know that this is correct. So anyway, horizontal translations, if it's bigger than 0, you go to the right. If it's less than 0, we go to the left. And then C, we all know what C is. C is your vertical shift or translations, same thing, right? You can use translations or shifts. And if C is bigger than 0, then we're going up. And if C is less than 0, then we're going down, right? However many units. So if it says plus 2, we go up 2. If it says minus 3, we go down 3. Pretty straightforward. And all of these rules apply the same way for every type of function that we have, which makes it really nice. You only have to remember these rules once and then just know them for every type of function. You don't have different rules for different functions. It's all the same. So let's go ahead and we'll look at some examples. Let's say I have y equals 2x minus 3 squared plus 1, and I want to graph this. Well, what I can do is I can start off by graphing the parent function, right? The parent function is just the original y equals x squared. So y equals x squared, I'll just label it like that. And let's say I want to do this one step at a time. So the first thing that maybe I want to apply is this 2 on the front that I'm multiplying. It's always a good strategy to apply your stretches, compressions, and reflections before you apply any of your shifts. At least if you're doing this one step at a time, that's the way you should do it. So I have a 2, so that's going to make it twice as tall and skinny, right? So vertical stretch, it's going to look like that. So this is y equals 2x squared. And then for the next part, if you want, you can do both the shifts at the same time. We can go 3 to the right and up 1. And we can do that by moving the vertex, right? So the vertex was here at 0, 0. It's going to go 3 to the right and up 1. So it'll be somewhere here. So this orange graph, we're just going to move it up to here. So now this blue graph here, that is your y equals 2 x minus 3 squared plus 1. So that blue one there is your final answer. And so be sure to clearly label which graph is your final answer on a test if you're doing one step at a time like I am here. Okay, let's do another example. Let's say I have y equals negative square root x plus 4 minus 5. We'll do the same thing, right? We'll do one step at a time. And we'll start with our parent function, which looks like this. This is y equals square root x. It starts, of course, at 0, 0 and goes up to the right like that. Now, like I said, you want to do your reflections and stretches and compressions before you do any of your shifts, right? So what kind of stretches or compressions do we have here? Well, we don't really have any. We just have this negative on the front, which indicates a vertical reflection or a reflection in the x-axis, right? We're going to reflect down. So you're going to get something that looks like that. So this is y equals negative square root x. Just the mirror image, just flip down like that. Next, we want to do our shifts or translations, right? The plus 4 here indicates we're moving 4 to the left, so to negative 4. And the negative 5 indicates we're moving down 5, negative 5. So this down here is your new starting point. Instead of at 0, 0, you're down here. So we're going to draw that same orange curve, but it's moving to here, just like this. So that's y equals negative square root x plus 4 minus 5 is that shape right there. And that's your final answer. Now, before we move on to another question, let's just talk about these square root functions a little bit, because I said before that sometimes you could have a reflection horizontally as well. And we had never really seen that before too much, especially with quadratics, because they're symmetrical. But if you notice, the square root function is not symmetrical, right? Square root function goes in one direction like this, right? That's y equals square root x. And in that last example, we had a vertical reflection. We came down like this. We had y equals negative square root x. Well, that's because that negative's on the outside, right? It's a vertical reflection. We could have had the negative on the inside, and that would have caused a horizontal reflection. Y equals square root negative x would look like this. And you can probably guess what's going to happen if I have both a negative on the inside and outside, a horizontal and a vertical reflection. You're going to get a graph that looks something like this. Y equals negative square root negative x. You're going to get this instead. They all start from 0, 0. They all go in their own direction. So this is why it's important to look for the negatives, see where they are, and how they're impacting your shape, because you could get wildly different answers. Okay, with that in mind, let's go to another example. Let's say I have y equals negative a half, absolute value x minus 4 minus 5. And we'll start off the way we always do. Draw your parent function. Absolute value function is just a big V like that. So the first thing we do is apply your stretches, compressions, and reflections. Well, you have a compression here, right? You have a vertical compression of 1/2. So that's going to make this thing half as tall at every point. So it's going to look something like this. So that's y equals 1/2 absolute value x. But you don't just have the 1/2, you also have a negative, right? That negative is a vertical reflection. That's going to reflect you down. So you're actually going to look something like this. This is y equals negative a half absolute value x. And then from there we can finally do our shifts or translations, right? We can go 4 to the right, and we can go down 5. So I'll move 4 to the right, that'll maybe be over here, down 5, maybe right there. So instead of starting at 0, 0, you're starting over here. So this blue line is going to move down here, and you're going to get this general shape. That's y equals negative a half absolute value x minus 4 minus 5. And that's your final answer. Okay, let's do an exponential. Let's do y equals 4 times 2 to the exponent negative x minus 1 minus 1. Now you might be saying, hey, you said I don't have to remember a whole bunch of different rules. They're all going to be the same. And yeah, this one is the same. It looks a little different because exponential functions look a little different, right? That's just the way they are. But if you look closely, you can see that the same rules are going to apply and the same patterns are present for this function. Let me show you what I mean. If you look at your x value up here, right, it's in the exponent, yes, but in the past you could always look at your x value and you could say, what number am I adding or subtracting to x, right? Here's negative 1. That's going to indicate your shift left or right. This negative 1 on the end of the function, that's going to indicate your shift up or down. This 4 on the front, that's going to indicate a vertical stretch. This negative in front of the bracket containing your x, that's going to represent your k value, right? That's going to be a horizontal reflection. So with all this information, you can interpret these numbers the same way you would otherwise with any other type of function, right? So let's go ahead and let's try to sketch this. We'll start with the parent function, y equals 2 to the x, which has a y-intercept of 1, right? And we'll start applying one transformation at a time. If you recall, we always apply our stretches, compressions, and reflections first. So let's start with the 4 on the front, right? This vertical stretch by a factor of 4. That's going to make our shape taller everywhere, right? 4 times as tall. It's going to look like this. And it's going to have a y-intercept of 4 now. Okay? So that's y equals 4 times 2 to the x to start. Now let's introduce this negative on the front. What's that negative going to do? Well, that negative, as we said, was a horizontal reflection. So we're going to flip sideways, right? So instead of this orange graph here, we're going to have this yellow graph, the exact same shape, but it's been reflected sideways. It's the mirror image. This is y equals 4 times 2 to the negative x. Now we can apply our shifts, right? We're going 1 to the right and down 1. So we can move this whole shape down 1 and 1 to the right. Now this might be a little bit tricky to figure out what this is going to look like because we're going down, yes. So like this y-intercept here, for example, is going to go down somewhere here. But then when we move to the right, the y-intercept is going to now be higher because this shape is moving to the right, right? So it can be a little bit tricky to figure out exactly how to draw this. For now, I'll draw it like this because even though it's moving down, it's also going to the right. And so that blue line there I will call y equals 4 times 2 to the negative x minus 1 minus 1. So that will be our final answer. And it's going to have a y-intercept up here above 4. And the reason I know it's above 4, I'm going to show you actually right now what I did. So to solve for the y-intercept, you might want to do this work on the side. We simply set x equal to 0 and solve for y, right? Just like we always do. So y equals 4 times 2 to the negative 0 minus 1 minus 1. Well, here you have negative 1 times negative. That's positive 1. 2 to the 1 is just 2. 2 times 4 is 8. 8 minus 1 is 7. So the y-intercept is at 7. So up here on your graph, this should be at 7, which is clearly above 4. So even though we're moving down, since we move to the right, that moves your y-intercept up to 7, right? So that would be what your final answer looks like. And if you wish, you could also label the x-intercept, right? You could set y to 0 and solve for x. So you could say 0 equals 4 times 2 to the negative x minus 1 minus 1, just like that. Move 1 to the other side. So 1 equals 4 times 2 to this. Divide both sides by 4. So 1/4 is equal to 2 to the exponent negative x minus 1. What's really nice about this question is you can write 1/4 as a base of 2, right? It's 2 to the negative 2. 2 squared is 4, negative is 1 over 4. So you can rewrite this as 2 to the negative 2. And the reason that's so nice is because that's equal to 2 to the negative x minus 1. Because they have the same base on both sides, the exponents must also be equal. And so we can say negative 2 equals negative x minus 1. And if we continue to solve this, get rid of the negatives, 2 equals x minus 1, bring the 1 to the other side, 3 is equal to x. So that's your x-intercept. So on this drawing that we did up here, this blue line would continue down and it would cross at 3. So if you were trying to draw your final answer, I would maybe do a new sketch separately, make it nice to scale, label your x, y intercepts, and then draw it. Another key part of this question is the horizontal asymptote. If you recall, exponential functions, at least the parent function y equals 2 to the x, has a horizontal asymptote at 0. Because there is a negative 1 here, what that does is it actually lowers your horizontal asymptote to negative 1. So at negative 1, you have this horizontal asymptote, which your line gets closer and closer to but never touches. And so if you were just graphing this from scratch, this is what I would do. I would find the x and y intercepts. I would recognize that the horizontal asymptote is at negative 1, and I would just put all that information together. I would say, here's negative 1. I said my x-intercept is 3. I said my y-intercept is 7. So those are 2 points that I have. I would connect them like this. I would draw that line like that. This line's going up like this. This looks a lot better as a exponential function. Still not perfect, it's a little bit sloppy, but this would be a much better representation than what I had drawn up here, right? Not quite as clean and neat. So that's my recommendation if you have to graph an exponential function. Let's do one last function here. Let's do y equals 1 over x plus 2. So now you have a rational function, and actually it's a specific type of rational function. It's called an inverse function because you have 1 over something that has x in it, right? 1 over x. So if you wanted to graph 1 over x plus 2, you could start off with graphing 1 over x. If you recall, 1 over x looks something like this, where you have an asymptote on the x-axis and the y-axis. You have a vertical and horizontal asymptote. This plus 2, because it's on the end of the function, it's on the outside, everything moves up 2. And that includes your horizontal asymptote. So that's going to be up here at 2. And so your new function looks like this. You have a curve up here, so that moves up 2. You have a curve here. This one moved up 2. So this blue one would be y equals 1 over x plus 2. We can look at a more complicated example of a rational function. And there will be a whole unit on graphing rational functions, but for now this is just a little bit of an introduction using transformations. Let's say you have y equals 1 over x minus 1. We draw our xy axes like this. Because this minus 1 is next to your x, you can think of it as being inside the function. That's your d value, right? X minus 1. So that means we're moving 1 to the right. So your original function, 1 over x, looked like this. But now we're moving 1 to the right, and that includes the vertical asymptote, right? There used to be a vertical asymptote here, but now it's moving to the right one, so your new vertical asymptote is over here. And so while that moves, all the curves move with it. So you now have a curve like this, right? It's this curve moved to the right, and you have a curve here. It's this curve we've just moved to the right. And so that's a relatively simple way of coming up with your graph, right? X minus 1, so we just move to the right. You could also have other things, other types of transformations. You could have y equals negative 1 over x. And I'm not going to draw the original. I've drawn it twice already. We know what it looks like. But a negative on the front suggests a vertical reflection. So the part that's down here is going to go up, and the part that's up here is going to go down. So you're going to get a graph that looks like this. It's kind of the opposite of what we usually have, right? If I have y equals 1 over negative x, and I want to graph this, well, now the negative is with my x. That represents a horizontal reflection, so reflecting sideways. So instead of like this, it's going to reflect sideways, and you're going to get this. Now, hang on. These two graphs look exactly the same as one another, and they absolutely are. And that's because algebraically, this statement and this statement are equal to each other, right? Remember, you can always simplify a fraction by moving a negative from the bottom to the top, right? So those two expressions are equal. That's why their graphs are equal. So it's kind of similar to how in the past a quadratic function, if there's a horizontal reflection, it doesn't change anything. Well, for these functions, for rational functions, their neat little thing is that if you have a vertical reflection and a horizontal reflection, they both result in the same sort of change. So keep that in mind.